Right here, this matrix right here represents this rectangle. The points are 12, 5, which would be here, and then 12, 2, which would be here, and then 6, 2 here, and 6, 5 here. Notice that they, when you list them here, they go in order. If you didn't put them in order, then you'd actually be writing something that looked like this or something else. In order to make this a rectangle, you put them in order so that you're actually tracing from here to here, from here to here, from here to here, and then from here back to over here. And then the instructions said transform this rectangle by reducing it by a factor of 0.9 and rotating it 30 degrees counterclockwise. And then you're to write a 2x2 matrix that does the rotation and the dilation. So let's look at what the result of that is. Here we go. This is the 2x2 matrix right here. Notice that 0.9 is on all the elements. That's your dilation. And what happens here is you put the cosine of the measure of the angle counterclockwise that you're trying to rotate by. In this case, it's 30 degrees. And underneath here, you put the sine of 30 degrees. In the second column, you add 90 degrees to both of these. So this is 0.9 cosine 120. This is 0.9 sine 120. When they put the numbers into their calculators, this is what they came up with here. So basically what number 2 was to say, go ahead and apply it and see what happens. And this is what happened. It actually rotated 30 degrees counterclockwise and got just a little bit smaller. Okay. If you put these into your calculator, right, this and this, these are the numbers you would get back. And if you had set it so that you only saw one decimal point, you would get this. And this is what's actually graphed here. The first point is 7.19.3. So here's 7, a little bit more than 7, right? And a little bit more than 9 over here. And then 8.5, 7.0, that would be here. 3.8, 4.3, that would be here. And then 2.4, 6.6, that's over here. So nothing's perfect. In terms of graphing this, nobody's expecting you to be able to graph it perfectly, but you start to see what happens when you put those numbers in and start to get the transformation you're looking for. Let's go back. Number 2 says to go ahead and set it and show exactly one decimal place and calculate this and then plot it on the figure. And then the image matrix saying store it as E and apply the transformation to the image matrix by calculating this. So in other words, what it's telling you to do is to use the result that you got and then apply A again, okay? And then it says to store that as E and get a third image and plot it on the figure. So let me show you what that looks like when you're doing it. You'll notice that it continues to sort of wrap around here and then here, but also notice something else, right? Although they told you to store it and then redo the multiplication by A, check this out. If you're doing A times D, this is what you get. If you're doing A times D, remember that the multiplication in matrices is associative. So there's no reason you can't multiply the two A's together first. A times D, okay? And then if you're going to do it a third time, it's A times D. You can put this in your calculator. Once you have the matrix in, you can put A, and then you've got the little button that's a caret, and the 3, and you wind up getting A cubed. And if you multiply that result by D, this is what you should get. And the thing to notice is what's happening here. Little by little, you're rotating around 30 degrees, but you're also making this smaller. And so the distances are also smaller. You started, if you were just rotating this, it would be going all around like this. But since it's getting a little bit smaller each time before it rotates, or as it rotates, you wind up getting a little bit smaller and a little bit smaller, and your arc here is getting smaller. So ultimately what happens, if you put this in, for those of you who have your calculators out, right, take the original matrix, this one right here, this is your rectangle, and take A, and instead of multiplying this by A and then by A again and then by A again, multiply it by A raised to the 50th power, and see what you get. It should be, when you get it, it should be that this sort of gets so small and comes so close that ultimately all of the points are 0. In other words, the rectangle gets so tiny that the distance from one vertex to the other is essentially 0. This one here, right? They give you another thing here. Oh, it's a dart. That's what it is. It's like a little arrow. So anyway, it's drawn here. And then it says, go ahead and make a transformation matrix that looks like this. Do the first few iterations and go all the way, and show what it would look like. And then sketch the pattern. Where is it going to go? What's it going to do next? And what it looks like is this. Here's what it looks like. It starts out up here, right? Here's your transformation matrix, your dilation matrix. Here's your rotation matrix. They put them all together here. You use that on your pre-image. You wind up with this, and then you do it again, and then you do it again, and then you do it again, and then you do it again. And look what happens. Little by little, it gets smaller, and you can see it's even starting to point where it's headed. The real thing here is what happens if you put in this transformation matrix raised to the 50th power and multiply that by this polygon matrix, right? The matrix that represents your pre-image. And you can sort of tell what's happening here. It's getting closer and closer and closer in here. This is called fixed point iteration. This is called, rotating around to a fixed point. And what's important about this is it's what happens if you do things an infinite number of times. Sometimes you get surprising results. You would think that no matter how many times you shrank something by 95%, right, or shrank something to 95% of its original size, it would never get to the point where it didn't exist. It does if you do it infinitely. I believe I've shown you the 0.9 repeating thing. Have I shown you that? Do you think that's true? So now watch me prove that it is. Okay. Let's call this X. And let's multiply it by 10. So if I multiply this by 10, I'm going to get this. If I subtract both sides from each other, here, all of the infinite number of nines are just going to fall away, because there's, for every one of these nines, there's one of these nines I'm subtracting, except for this one. So I'm going to get 9 here. And over here, I'm going to get 9x. If I divide both sides by 9, I get 1x. 1 is equal to x. So as much as, you sort of hate this, and I don't blame you if you do, as much as this sort of hurts your mind, this right here, 0.9 repeating, is actually equal to 1. And you say to yourself, well, how can that possibly be? How is that possible? And the answer is that when you start talking about things that are infinite, infinitely long, infinitely many nines, weird things start to happen. Right in here, this concept in here, the concept that says if you put an infinite number of nines here, the difference between this and this is 0. That's sort of what's at the heart of calculus. It's where calculus starts. Okay. Another one of those things that happens, right? There's an ancient Greek named Zeno. And back in the day in Greece, he said, you know what? Here's something to think about. If you want to go from here to here, it's impossible. You can't do it. You're never going to make it. Why? Because in order to go from here to here, you have to get to the halfway point. And then once you're at the halfway point, in order to get from here to here, you have to get to the halfway point again. And then once you're here, in order to get from here to here, you have to get to the halfway point again. You're starting to get the picture, right? So as long as you keep having to go halfway, you're never going to make it, because there's always going to be this little tiny difference between where you are and where you're going. You're never, ever going to get there. Okay. So of course that's annoying. It's called a paradox because it's not true in the physical world. So then the question is, where's the difference here? What's different about this? And the answer is the same as up here. This notion that the limit of this, as you approach an infinite number of nines, is 1. And the limit of this, let me put it this way, if you are actually talking about this, then what you're talking about is, whoops, that's not where I wanted to be. What you're talking about is 1/2, right, plus 1/4, plus 1/8, plus 1/16, et cetera, et cetera, et cetera. An infinite number of additions. And the fact is that when you add all of those up, you wind up approaching 1. You have a limit of 1 as you get towards infinity, as you start to add an infinite number of these together. The sum, if I put little plus signs in here, The sum of this, we say, is equal to 1, because really what it is the limit of all of the sums. If I start with this, and then I take these two and add them together, then I take these 3 and add them together, then I take these 4 and add them together and put those sums in a row, those will get so close to 1 that it's inconsequential. The difference doesn't matter. Okay, and again, in here is the heart of calculus, or at least not the heart, maybe the seed, the germ that gets the whole thing rolling. And this is just sort of another example of that. Okay, this thing right here, where if you do this enough times, all of the vertices converge and they become 0. Okay. And it is possible to prove that algebraically, which I'll show you in a little bit, but right now I just sort of want to let this sink in. Okay. This is specifically why I include this in the discussion of matrices. And frankly, this is why I think matrices are worth teaching in this class, because it really does help get your mind ready for calculus, which is sort of the point of the class.